In the last lecture, we discussed a very unusual event that occurred around 600 million years ago. At that time, almost the entire Earth was covered with ice, and it is called snowball Earth. If you recall, the simple energy balance model predicted that such an event can occur, but nobody thought that it actually can happen because they thought that if the entire Earth is covered with ice, then there is no chance for life to exist on Earth, because the life that we know on Earth depends primarily on photosynthesis. So they thought if that had occurred, life based on photosynthesis would have disappeared. But 30 years ago, geologists were able to provide evidence that glaciation had occurred on rocks which were near the equator 600 million years ago. Okay? And the question then arose, why did the snowball Earth event occur 600 billion years ago and not in the last 600 billion years duration? You remember that we discussed that there were 10 major ice ages in the last million years. Okay? But in none of those ice ages, the ice went beyond from the pole to more than 40 north. It didn't come near the equator. Okay? The question is, why didn't these ice ages continue to grow and become snowball, and why did it happen such a long time ago? Okay. So understand that we looked at this important relationship between incoming radiation and the amount of carbon dioxide on Earth. Okay. Remember, carbon dioxide is the most important greenhouse gas on Earth after water vapor, but water vapor's amount in the atmosphere depends on temperature. So it is very much dependent on carbon dioxide creating that high temperature. So carbon dioxide is the dominant controller of the Earth's climate. And when the Earth began 4.6 billion years ago, the atmosphere was almost all carbon dioxide. Okay? And over a long period, carbon dioxide declined, oxygen went up. So today we have around 400 parts per million, but about 600 million years ago, it was somewhat higher. The second thing is the incoming radiation. Today it's around 1360 watts per meter squared. But if we go to Earth's past, the sun's output was somewhat lower. Sun is a major nuclear fusion reactor. The reactor started 4.6 billion years ago, and as the reaction grew, the solar luminosity or the radiation went up. Now this we know from study of many millions of stars in our galaxy, that depending on the age of the star, its radiation output increases. Okay? So the question is, what combination of incoming solar radiation and carbon dioxide will permit snowball Earth? Okay? So if the solar luminosity is very low, of course Earth will be covered with ice unless CO2 is very high. So in the beginning, carbon dioxide was very high, so snowball Earth was prevented. Today snowball Earth is not going to happen because luminosity is very high. So there was a period around 1 billion years ago when these two conditions were suitable for snowball Earth. A simple energy balance model can be used to infer what combinations are necessary, but people don't trust a simple climate model because it does not include ice sheets or the way snowfall occurs, the way snow melts, ocean circulation. There are so many things which control Earth's climate. So, simple energy balance model, although useful as a beginning, cannot really tell you under what conditions snowball Earth could occur. For that, you need complex climate models. The second thing is we also realize that if all the continents are around the equator, the conditions are more suitable for snowball Earth because most of the radiation on Earth falls in the tropical region. If the tropical region contains a lot of land, land has a higher albedo than ocean, so it will reflect more radiation. Albedo will be higher, so the chances of Earth being colder will be higher. Okay? So, these two factors played a role, and we now look at how climate models are able to simulate a snowball Earth. Now, when initially full coupled ocean atmosphere model with ice sheet and everything was used for simulation, they had difficulty in producing a completely ice covered Earth. Simple models with a mixed layer ocean, that is no circulation, can be made to freeze at the equator. A more sophisticated model with full ocean circulation and primitive sea ice failed to form sea ice at the equator. Okay? So, some of the models said the levels of CO2 necessary to melt the global ice cover would be around 130,000 parts per million, which was considered to be too large. Remember, there are two issues. One, these models should be able to produce a completely ice covered Earth. Secondly, if you increase CO2 in that model, at some point all the ice has to melt, because after all, after the last major snowball event 600 million years ago, Earth came out of the snowball and life thrived further. Okay? As a matter of fact, biologists consider the snowball Earth to be a major event which enabled life to develop more complex form, okay? The multicellular life. Before that, life forms very simple, but under conditions of very cold temperature, the evolution came up with a solution which was more complex than what it was earlier. So, snowball Earth is very important now in the discussion about how life evolved on Earth. Now, I am going to talk about one of the models developed by the European Centre called ECAM5, coupled to the Max Planck Institute ocean model. It initiates snowball Earth around the time of the Merovingian age, that is 635 million years ago, for incoming solar radiation of 1285 watts per meter squared, which is lower than the present, which is to be expected, and when carbon dioxide is reduced to 400 parts per million. One problem is we do not have any proxy data to tell us what was the concentration of carbon dioxide around 600 million years ago. We have no data. Okay? So, we have to guess and vary it and see. In contrast, last million years where we had ice core data which told us what was the amount of CO2, we have no data going back to 600 million years ago to tell us what was the concentration of the carbon dioxide in the atmosphere. Okay. Now, I am going to show you a few simulations from the ECAM5 atmospheric model and the Max Planck Institute ocean model, okay, where we are showing here the annual mean global sea ice cover in response to an abrupt decrease in the solar constant from 100 to 94%, which is the value we believe that was there 600 million years ago. Okay. What do you see? What you see that if the CO2 concentration was 278 part per million, the Earth rapidly achieved a large ice area, 100% ice area. Okay. But if you increase the CO2 concentration to 556, double 278, it did not do it for almost 1,500 years. But then when it was reduced 500 ppm, it immediately went up. Okay. So you can see that the requirement for snowball Earth in this model is that the amount of CO2 has to be less than 556 parts per million, because when values like 1112 or 1668, these two values, the sea ice didn't increase. So sea ice covers the whole Earth only in a combination of CO2 amount and solar constant. In this model, solar constant has to be 94% of the present value, and the CO2 concentration has to be 400 parts per million or lower. Now, here is another simulation in this model done with various lower concentration of solar radiation and various concentrations of CO2. Okay. And you can see that with 6% lower concentration of solar radiation and 278 parts per million, immediately you get a snowball Earth. But instead of 6%, you made it 4.5%. Then it takes a very long time. Okay. So it's very sensitive to the incoming solar radiation. Now, further simulation was done keeping the carbon dioxide constant and varying the solar radiation to demonstrate that the radiation has to be 6% below the present. And keeping the radiation 6% below the present and varying CO2, it was shown that in this model, the full snowball Earth is achieved only at around 70 ppm. Okay. Now, the issue here are what is the temperature in the equatorial region. Okay. So, here in this example, in the equatorial region, in June, July, August, there is no ice cover. But in December, January, February, there is ice cover. Okay. So, seasonal cycle is there, that is okay. So, Earth was covered with ice in December, but not in June, July, August. But if you reduce the concentration of carbon dioxide to 50 ppm, it's mostly ice covered in winter, but still there is a small time in summer when it is not ice covered. Okay. So, this result many biologists will be quite happy, which means Earth was not ice covered throughout the year, was ice covered for a part of the year, which means life could have managed to survive the snowball Earth. And if you compare the simulation with two different models, CCSM4 and CCSM3, there are differences. So, I want you to realize that the results are sensitive to the model used. Now, why is that? It's because of the assumptions about the sea ice albedo, the snow albedo, and we don't have accurate data on how sea ice and snow albedo will be in the past. Okay. Now, sea ice albedo depends upon how much of the sea is covered with snow. If there is no snow on the ice surface, ice is somewhat transparent, so it will not reflect as much. If it is covered with snow, then it will increase. So, for example, in CCSM4 they assume higher sea ice albedo than CCSM3, so they will get a different result. And observation shows a range of values in the Arctic. Okay. Of course, snow always has a high albedo when it is fresh snow. Okay. Now, all these results can also be understood through a simple energy balance model, where you can vary the solar flux here in the x-axis and vary the amount of CO2 in these three different curves, and look at where is the ice line. Okay, at what ice line is there? If ice line at 90 degrees, you have an ice free earth. If ice line is at the equator, this is 0. Okay. So, you can see that both these solutions are permitted, ice free and ice cover, for various values of carbon dioxide. Okay. Only when carbon dioxide goes above this, these are the values of carbon dioxide they have used in the simulation. Okay. 0.12 bar and 0.02 bar and very low amount of CO2. But you can see whatever the amount of CO2, there are still two stable solutions, the ice free and the ice covered. Okay. And the major issue is, when does the ice cover go past sign of around 0.5? Sign of 0.5 is of course 30 degrees. Okay. So, the issue is, in most models the ice cover as it increases does not extend beyond 30-35 degrees latitude to the equator. Okay. Beyond that it jumps. These are unstable solutions. Once the ice cover crosses this value, it will not stay there, it will straight away go to this. Okay. So, this you have to understand what governs this. Okay. This is a figure from the paper by Hoffman on snowball, and he also gets three solutions: ice free, ice covered, and a stable solution which is partly ice covered, the ice age solution. Okay. And so, for the amount of radiation coming in around 600 million years ago, he gets only two solutions. Either it is ice covered up to I would say 40 degrees north, or it is completely ice covered. And you can see that as soon as it comes around 30, it has no stable solution, it jumps to this value. And of course, it also depends on what is your continental configuration, where are the continents. So, if you put the continents where they were during the Marinovan period, then you will get the solution. So, here is one simulation, and for two different CO2, 10 ppm, very low CO2. Okay. So, then you look at ice thickness. Not only you have to know about the ice cover whole earth, how thick the ice is, because if the ice is very thin, life can still survive, because some radiation will go through. So, people don't know what the ice thickness is. You can see that if there is only 10 ppm CO2, ice becomes pretty thick. Okay. But if you increase the ice to the CO2 to 20,000 ppm, it starts melting. Okay. Now, you can see that the difference between two hemispheres, northern and southern, because of the difference in land coverage. Now, this is the problem that all these models face. What assumptions they make about ice with snow, usually high value, bare ice they use a low value, and open ocean of course is extremely low. And so they specify the albedo values. There are two examples from this study by Voigt et al. The albedo will change once the temperature goes above minus 0.1. So that is the melting of ice. So concerned about the survival of life, I have led some people to propose that complete ice coverage is not possible. You can have what they call slush ball, that is between around 25 degrees latitude and the equator there is water, not ice. Okay. So here you have shown that a slush ball would require very low ice ocean albedo contrast, okay, and would precariously close to this bifurcation point. So this is solution obtained by Voigt. He called this Zerbourn-Gand from the German word for slush ball. So he gets a solution where there is water between 20 south or 20 north and then ice beyond that. Okay, and so this is also considered a snowball earth because most of the earth is ice covered except near the equator. So only equator is above 0, rest of them are below 0. Okay, this is a model without continent, so called aquaplanet. It's easier to simulate this. And so this model has no aerosol. It has diurnal cycle, annual cycle and so on, but a solar constant is 95% and the amount of CO2 is 5,000 parts per million. That's pretty large. That could be the reason why they are getting a bit of no ice region near the equator because the CO2 is very large. Now there are papers which are come later which claim that fully ocean earth may not be there because they have found evidence that sedimentary rock deposited during these cold intervals indicate that there were dynamic glaciers and ice streams which flowed into the ocean. So there is one paper contesting the possibility of completely ice covered earth. So this debate is still not totally resolved. So some people have highlighted the role of ice sheet. Okay, the simpler models have no ice sheet; they have ice and snow, but they don't have ice sheet with the thickness and its movement and its ability to depress land. All that is not there. So there are people today who say that you have to include ice sheet to be able to get completely ice covered earth. So people have studied the duration of the snowball in billions of years and the amount of CO2. Okay. So various numbers are given here from various papers, and you can see that if you do not have a high CO2, you cannot get out of the snowball earth. One of the issues is, fine, the earth was covered completely with ice. What will it take to get it out? And the logic is that once earth is completely covered with ice, volcanoes will continue to emit CO2 and volcanic eruptions are so violent that the carbon dioxide will rupture through the ice and come into the atmosphere, and the CO2 will go on building up because there is no photosynthesis. So there is no carbon cycle to convert carbon dioxide to calcium carbonate. Okay, so this will go on. So question is, how high will CO2 reach, and at which point the high amount of CO2 will completely melt all the ice. So that was the issue a lot of people have looked at. Okay. So here is an example showing as the CO2 is increased, how the sea ice decreases in the model. Okay. So they are saying you will need around 1000 ppm of CO2 to reduce the ice cover from 100% to around 30%, which was what we have observed over the last million years. Okay. So you can calculate how much time volcanoes will take to take the CO2 from, let us say, 500 parts per million to 1000 parts per million. One can get some numbers based on that. Okay. So here also you can see that as the CO2 is increased, the global ice production goes on decreasing until it reaches 0. Okay. And so you can see that there is an abrupt change. For example, take this model ECAM5, up to 500 parts per million it is completely ice covered, and then it starts reducing. Okay. And it reaches, I would say, ice production of around 30%, which happened in the last million years, and it is around 4000 parts per million. So all these are used to come up with how long this snowball earth will be there before it is melted. So you can understand this also by the traditional method we discussed earlier in the course, by taking simple energy balance model and looking at the amount of CO2 here on the top in parts per million and the global mean temperature by various ice albedo conditions. Okay. As I told you, ice albedo is a very critical parameter, and so ice with not much snow will be 55%, ice with a lot of snow will be 65%. So you can see that in this model, if the CO2 is very low for the incoming radiation of 1285 watts per meter squared, if the CO2 is below around I would say here 50 parts per million, it will be completely ice covered, while if it is above 62,000 parts 62,000 parts per million here, it will be completely ice free. In between you will have various solutions with various amounts of ice cover. So the other thing people have looked at is the location of the continent. I told you that if the continents are closer to the equator, it is easier to have snowball. Okay. So here is an example of how much CO2 is required, depends on to remove the snowball earth, depending on whether continents are at low latitudes or at high latitudes. So if the most of the continents were the tropics, this would not commence until CO2 levels are substantially lower. Now let us understand this from the energy balance perspective. We have discussed earlier that the incoming solar radiation is a function of latitude, because in the polar region you have 6 months of no radiation. So the annual mean radiation is much lower in the solar region than in the tropics, right. So if the ice cover is there up to some latitude phi I, okay, and starts to increase and come towards the equator, then there is more area here than here. Okay. So there will be a tendency for ice sheet to grow, okay, because as the ice sheet grows, albedo of the earth will increase, because this is higher area than here. Okay. So as the ice sheet grows, more and more of the earth's area will have higher albedo, and that will make the Earth tend towards higher ice cover. But there is a counteracting phenomena, which is transport of heat from the equator to the pole, and we showed that correct way to do it through a diffusion model, but we use simple model where we said heat transport from the equator to the pole is the temperature of latitude minus the global mean temperature multiplied by a constant c, right. So, this tendency for the ice sheet to grow will be counteracted by the tendency for the heat to be transported to the. So, the melting of the ice will be due to heat transport to the equator, and growth of ice will be due to increase in albedo. The two will interact, and so because the Earth is a sphere, this tendency will be unstoppable if the ice grows beyond 30 degrees east. So, to show that, I would show you inequality. That inequality comes as follows. This is a change in albedo as you approach the equator. This is the incoming radiation at that latitude. This is the cosine to take care of change in area, and this B is that formula for OLR was A plus BT. If it is less than heat transported by meridional circulation, remember dt dphi is negative because temperature is high at the equator and low at the poles. So, as you go from equator to poles, temperature decreases, so dt dphi is negative. So, this quantity is positive. So, as long as this is less than this, then the ice will not grow. Okay. Only when this exceeds that, then it will tend to grow. So, there is some critical latitude. Once you go to that latitude, Earth will inevitably go to a full snowball Earth. This concept is called large ice cap instability. Once you have a large ice cap, it will be tend to be unstable because as the ice cap grows, it will increase the albedo of the Earth. Okay. And this value is for present condition around 33 degrees. Okay. For example, in the last million years, when the ice grew maximum extent, it was up to 40 north. If it had moved beyond 40 north and approached, let us say 33 degrees or 32 degrees, you would have had a snowball Earth in the last. We didn't have it because it didn't cross 40 north. Okay. So, we will continue the discussion in the next lecture to understand this feature.